Okay, so here's the second problem set, which is problem set 66, focusing on simplification of radical expressions and square roots of large numbers. So this is kind of a bit like a part two of problem set 65, where we're going to be trying to add some radical expressions, also known as roots. And in this first example, we have the root 18 plus root 8. And one thing you might notice right off the bat is that these are not like roots. It doesn't appear that we can do much with this, except that we can actually simplify these roots. And in simplifying these roots, we might actually find that we can combine like roots after that process. So remember that if I'm going to start with 18, if I was going to simplify that root, I can prime factorize that 18, and I recognize, okay, 2 times 3 times 3 is the prime factorization of 18, and I can actually take the square root of 3 times 3, which is just 3, leaving the 2 inside, which makes this actually 3 root 2. I'm going to do the same thing with root 8. I'm going to prime factorize over here. And I have 3 2's, but I can root one set of 2 times 2's, which actually makes this 2 root 2. And at the end of this, we actually do have like roots. These are both being multiplied by root 2. And we know from problem set 65 that we can just add the 3 and the 2 that's on the outside of this radical sign here, and we get 5 root 2. All right, we have another example. Again, noticing right off the bat, there's no like roots that are obvious here, so we have a little bit of work to do. I'm going to start with the root 27, and I'm going to see if I can simplify that a little bit. So 3 times 9 gets me 27. 3 times 3 gets me 9. So I have a pair of 3's here, which means I can root that, putting the 3 on the outside and leaving one of those 3's inside the radical sign. For this situation here, we actually have a negative 3 times root 18. Now I'm going to focus on the root 18 here and see if what I can pull out of there. And whatever I actually do end up putting outside the radical, I'll multiply by negative 3 when I simplify it. And I'll kind of show you what that looks like. So here we are. We're prime factorizing. We recognize, okay, we got a set of 3's here. We can pull one of those 3's outside. And then I'm going to do 3 times negative 3 to actually make this negative 9 root 2. Again, and that's because we already have a negative 3 outside that we need to multiply that 3 times that already existing negative 3. And we're going to have to do the same thing with this negative 6 here. So let's prime factorize the 45. All right, we got a pair of 3's. We'll pull one of those out. So we got negative 18. Because I had to do, excuse me, I made a mistake there. No, I didn't. I pulled out one of the 3's, 3 times negative 6, which is negative 18. And then I leave the 5 inside. Now, so at this point, there's not a whole lot else we can do. So we're going to leave it. We don't have any like roots. Okay, now we're going to get into some square roots of really large numbers. What I like to do with these is that I really like to just prime factorize. So I give myself plenty of room with root 50,000, and I'm just going to start prime factorizing this thing. And it might make sense to try to, break it down quickly. So 5 I know is a prime factor, 10,000. So I'm going to see how many 5's I can get out of here. So now I'm down to 2,000 pretty quickly. Maybe I'll keep going with my 5's. So 5 times 200 would get me 1,000, which means 5 times 400 would get me 2,000. I'm going to just keep going here. 5 times 8, 2 times 4, and 2 times 2. So I need to find all the pairs of squares in here, really. I got 2 sets of 5s, 2 sets of 2s, and then I have the lone 2 right here. So what ends up happening is that I will take one of each of these and multiply them together, put them outside the radical sign. So 5 times 5, which is 25, times 2, which is 50. And I get 50 root 2. 2 is the only one that doesn't have a pair. Now, one of the things that I always like to point out to people is that if you get to this point where you're trying to find the square root of a pretty large number, and you get something like 50 times root 2, you can always take a calculator and check these two, right? Put the square root of 50,000 into your calculator, see what that decimal is, and then do 50 times the square root of 2, and you should get the same decimal if these are in fact the same. So just kind of something to keep in mind as you kind of move forward. All right, 40 million, let's do it. It's going to be quite a lot of prime factorization, but we can totally do it. Let's see. How about 2 and 20 million? Whew. 2 and 10 million. $5 and 2 million. Lots of zeros. 2 and 1 million. We're getting there. 5 and 200,000. Myself more space. 5 and, well, it would be 5 times 20,000 gets me to 100,000, so 5 times 40,000. 5 times 8,000. Oh man. 2 times 4,000. 2 times 2,000. 2 times 1,000. 5 times 200. 2 times 100. 5 times 20. 5 times 4. And 2 times 2. All right, we got to be really careful here. Now we got all the prime factors on the outside of this ginormous prime factorization. I got a pair of 2s here. I got a pair of 5s. I got another pair of 2s here. We got to be really careful. I got another pair of 2s here. Man, this 5, go with this 5 over here. Oh man, a lot to keep track of. And we got another set of 5s here. Okay, I got another set of 2s up here. And now, my job is to find the root of each of these things. So I'm going to start up here. I might even, just for organization's sake, I got the root of these 2s. So 2 times, we need one of these 5s over here. So write that down. We got these 5s here. It kind of goes all the way down to this part. So that's another 5 that we're rooting. We got a 2 from this set of 2s. We got another set of 2s. Another set of 5s. And one more set of 2s. And I kind of ran out of space here, but the thing that's still in the root that's being multiplied by all this stuff, the only 2 that don't have a pair is the 5 times 2, which is 10. These 2 right here. So we still have root 10 there. And now we just need to multiply all of these prime factors together. 2 times 5 is 10, times 5 is 50, times 2 is 100, times 2 is 200, times 5 is 1,000, times 2 is 2,000. So we end up with 2,000 root 10. And that should be equivalent, reminding us what we are actually going for up here, to the square root of 40 million. All right, 700 million. Give yourself plenty of space. Here we go. Seven and 100 million. Ten and 10,000. Oop, I gotta break the 10 apart a little bit more. 2 and 5. Oops, I made a mistake here. Let me restart. This is actually 700 million. Sorry about that. And we had 7 and 1 million. 100 million, rather. And let's see, we have 8 here. So my question is that can we actually find the square root of 100,000, or 100 million, rather? Because if we can, if that's a perfect square, then we can actually really jump to the chase. So if you actually think about it, what times itself gets you to 100 million? $10,000. So because this is a perfect square, I'm going to save myself all that work that I did before, and I'm going to recognize that, yeah, actually, 10,000 times 10,000 gets me to 100 million. And because of that, I'm actually going to pull my 10,000 outside because I can find the square root of that, right? And I'm going to leave the 7 on the inside. So a little bit of a shortcut there. All right. So it's all about finding perfect squares within the factors of these larger values. Give this a shot with the practice problems and see how it goes.